Well, good afternoon. Since there's no questions, let's move back to the set of calculations that we were working through. So we looked at some basic calculations. You'll need that information for the homework. And I want to move to looking at mass and energy balances. And we can write that in words, stating that the mass rate of accumulation is equal to the mass rate in minus the mass rate out plus or minus the mass rate of any sources or sinks. So let's think about this in terms of a model. And we can think about this as, let's think of this in terms of it's evening, you've got a stove, burners, and you're cooking dinner. And we're going to assume that this is a gas stove. So if we have a gas stove, that gas stove will produce a number of pollutants, including carbon dioxide, nitrous oxides, incomplete combustion, also some carbon monoxide. So let's think of that, and we'll just write this in terms of CO2. And we want to do a mass balance on that CO2. So in order, if we want to do that, we want to write, start this way, the change in mass with respect to time is equal to, we have windows or ventilation, so we have a mass in from that ventilation. You have mass leaving through ventilation. We have sources. So we have a mass rate from the stove. Are there any other sources of carbon? So we're looking at carbon dioxide. Any other sources of carbon dioxide?
The person cooking on the stove?
Mm-hmm. Any sinks for carbon dioxide?
If there's a house plant?
There's a house plant. I'm going to put some sort of a house plant here, and it's going to have some flowers, just to show that it's a house plant. Okay, that's a very big one, but so we can write a mass balance. Okay, we can make some assumptions. So, for example, if we assume that this entire space is completely mixed, we can then assume that the concentration at any point in this kitchen, so if we measure carbon monoxide anywhere in this kitchen, it is equal to the concentration leaving. We can simplify this term here because mass is equal to the concentration times volume. And our volume is constant. Hopefully your kitchen is not changing size in the midst of cooking dinner. So then we can write this as volume times the change in concentration with respect to time. So we can remove volume from the differential because we're assuming that it's constant. And that is equal to the rest of that equation. We can also make an assumption, perhaps, may or may not be true while you're cooking dinner, but we can make assumptions about steady state. And if the system is at steady state, what does it mean about this term right here?
Would that mean that doesn't change?
It doesn't. Exactly, it doesn't change. So this is equal to 0. Okay, so if you're at steady state, then the concentration as a function of time, or the change in concentration as a function of time, is 0. There's no change in concentration. Not likely while you're cooking, but that's true for a steady state situation. We will use these concepts throughout the course. So it's important to have a good sense of what it means for something to be completely mixed and what steady state means. So let's look at a number of examples. So in this case, we have a 1,000 megawatt power plant, and it's burning bituminous coal. And that coal has a sulfur content of 3% and a heat content of 30.48 megajoules per kilogram of coal. So that's how much energy we can extract essentially from a mass of coal. The efficiency of the power plant is 34%, and you're told that 5% of the sulfur ends up in the bottom ash, and the remaining ends up in the fly ash. So the fly ash is what goes up, would go out through the smokestack. And you're asked to determine the annual rate of SO2 emissions if there were no control technology. So let's start with a mass and energy balance. We have coal entering the reactor, the power plant. What are the outputs? During mass balance, what's leaving the system?
The bottom ash and the fly ash.
Okay, so we have bottom ash, and we have fly ash. What else? We're doing, in this case, we're going to do a mass and energy balance.
Oh, energy leaves.
So the energy leaving, and what forms does that energy leave?
Heat.
Heat. And what else? What are we doing?
Electricity.
Electricity. So this electricity here, when we talk about a 1,000 megawatt power plant, that's the energy produced. It's not the input, it's the output. So if our plant is 34% efficient, that means in terms of energy input, we need roughly 3 times as much energy into the system as what we get out in electricity. Okay. So then the energy in is equal to that 1,000 megawatts, and I apologize, let me see if I can erase some of that, divided by 0.34, and that is equal to 2941 megawatts. And a megawatt, we convert this is 2.2941 times 10 to the 6 joules. And this is, right, this is a comma there, not a, okay. So this, remembering a watt is a joule per second. Okay. This tells us how much energy we need to input into our system. We're inputting that energy in the form of what? What's providing the energy in? The coal, exactly. Okay, so if we have 2941, I don't even know why the eraser's not working now. 2941 times 2941 times 10 to the 6 joules per second divided by, this is where I need the heat content of the coal. And we said that that was 30.48 times 10 to the 6 joules per kilogram. And we're going to multiply that by 86,400 seconds per day times 365 days per year, because we were asked for the, the emissions on an annual basis. And this is equal to 3.04 times 10 to the 9 kilograms. So this is the amount of coal that we will need to supply to this power plant on an annual basis. How do we determine the amount of sulfur entering the system? Go back. We said that the coal has a sulfur content of 3%. So the sulfur in is 0.03 times 3.04 times 10 to the 9 kilograms per year, or 9.13 times 10 to the 7 kilograms per year. How do I determine then the amount of sulfur leaving through the smokestack? We said the bottom ash contained what percent of the sulfur? It's 95%. So the bottom ash was 5%. So the rest smokestack is 95%. So it's 95% of what enters. And that is 8.67 times 10 to the 7 kilograms per year. You're asked for the amount of sulfur dioxide leaving. Sulfur reacts with oxygen to produce SO2. That equation is balanced. It's a 1-to-1 ratio. So for every 1 mole of sulfur, 1 mole of sulfur dioxide is formed. So the sulfur dioxide out in the smokestack is equal to the 8.67 times 10 to the 7 kilograms per year. We have 1 mole of SO2 for every mole of sulfur. It's forming 1 mole of SO2 for every 1 mole of sulfur. And there are 64 grams per mole. That's the molecular weight of SO2 divided by the molecular weight of sulfur, or the atomic weight of sulfur, really. And that is equal to 17.3 times 10 to the 7 kilograms per year. If we had no control technology, this 1,000 megawatt plant would contribute roughly 17 times 10 to the 7 kilograms of sulfur dioxide to the atmosphere every year. That's why we need control technology. Any questions about that problem? So look at a little more complicated exercise. And in this case, you're asked to determine the concentrations. We're just going to focus on parts per million today, of the products formed from the combustion of coal with air. I'm going to make some assumptions. We're going to use this equation here to represent the chemical formulation of the coal. We will assume that air is entering the system at 50% excess. So we're providing 50% more air than what we would require based on stoichiometry. We'll use standard conditions, so 25 degrees C, 1 atmosphere. We'll assume that all of the nitrogen in the fuel forms NO2. We will assume that we have perfect combustion. If we have perfect combustion, what are our products? CO2, water. We'll assume we have NO2, but that NO2 is only from the fuel. The nitrogen that's in the air does not react to form NO2. So if we have perfect combustion, any of the nitrogen entering the system leaves as N2. So there's no additional N2 from the air, the nitrogen in the air. We'll also assume we have SO2. We're not going to worry in this case about particulate matter. We could actually continue this problem on and do further calculations in order. We have enough information to actually look at the particulate matter, but we won't do that today. So we have a formula for coal. We're actually not going to use the information for the ash because we're not going to look at particulates. So when we look at these reactions, carbon reacts with oxygen to form what?
Carbon dioxide.
Exactly. Hydrogen reacts with oxygen to form what? Water vapor, exactly. We have 2 oxygens, so we need 2 waters. We need 4 hydrogens. The nitrogen in the fuel reacts with oxygen to form NO2, and the sulfur in the fuel reacts with oxygen to form SO2. So we have 4 sets of reactions here. You're given the molecular formula. So if we have 70 moles of carbon, how many moles of oxygen do we need? We have 70 moles of carbon. How many moles of oxygen do we need? 70, exactly. And we produce 70 moles of CO2. If we have 100 moles of hydrogen, how many moles of oxygen do we need? And we produce 50 moles of CO2. Yeah. We have 0.2 moles of nitrogen in the fuel. So we need 0.2 moles of oxygen, and we'll produce 0.2 moles of NO2. And we have 0.3 moles of sulfur. We need 0.3 moles of oxygen, and we'll produce 0.3 moles of SO2. Okay. So the next thing we need to calculate is the amount of oxygen needed. And that is equal to the sum of the oxygen for each of the reactions minus the oxygen in the fuel. So we'll simply add up each of these terms right here. So we have 70 plus 25 plus 0.2 plus 0.3. And we have 1 mole in the fuel. Now it's O2. Remember, we're looking at O2. So it's 1 mole of O2, not 2. And that is equal to 94.5 moles. But we said that we needed 50% excess. So we'll multiply by 1.5. So we need 141.8 moles of oxygen added into the system. So good question. Why 1 mole of O2? Everything that we notice here, we're doing a mass balance on O2, and this is O2. Okay, so it's 1 mole of O2. If we were doing a mass balance on atomic oxygen, then everything here would be multiplied by 2, and then that would be multiplied by 2. Okay, but since we're doing the mass balance on oxygen, it's 1 mole. Where did the 1.5 come from? We said that air enters at a 50% excess. So if we need a 50% excess, we're going to multiply by 1.5. So if it was there's no excess, we'd multiply it just by 1. So this is because we need a 50% excess. Other questions? There's a lot of calculations in here, so please feel free to ask questions.
I have a question about the equation, the second one where we have 100 moles H plus 25 O2 yields 50 CO2. Why is it CO2 or is it supposed to be H2O?
Oh, sorry.
Was it supposed to be H2O?
Oh, thank you for catching that. Yes, that should be H2O.
Okay, thank you.
Other questions? Feel free to, if you say that I write something wrong, please tell me. I'd much rather correct it than let it go. So if you see something like that, please feel free to interrupt and ask. Now we need to calculate the amount of nitrogen. So in order to calculate the amount of nitrogen, how do we do that? So we needed roughly 142 moles of oxygen. How can I calculate how much nitrogen is in that air?
Is it from the ratio of oxygen to nitrogen?
Exactly. So we have 141.8 moles of oxygen, and air contains 79% nitrogen and about 21% oxygen. And that is 533 moles nitrogen. So the total number of moles of air entering the system is that 148.8 moles of oxygen plus the 533 moles of nitrogen. This is our power plant. Here we have 675 moles of air leaving. Oh, sorry, entering. Question is, how much is leaving? Now we need to look at those reactions. So now we're looking right here at these reactions here. So we have 70 moles of CO2, 50 moles of water, 0.2 moles of NO2, and 0.3 moles of SO2. Now we're adding, that's what we're producing just from the reactions of the coal with oxygen. We're also adding the 675 moles of air. So we've added that, but we calculated here this was the number of moles of oxygen that we needed. So it's the number of moles of oxygen that's reacting. So we're going to subtract. It won't. It won't let me write over where the captions are. So now this is equal, write it over here, is equal to 101 moles. So what's leaving here is 701 moles of gas. So we have 675 moles of air entering. We have combustion in the power plant. And then we have 701 moles of gas leaving that power plant. So we're looking at what's formed plus what entered the system in the form of air minus what's reacted in the form of oxygen. This oxygen here all ended up either as CO2, water vapor, NO2, or SO2. So that's why we're subtracting it. So now to get the concentrations of these pollutants, so remembering we have 101 moles of gas we're producing. We can look at CO2. We produced 70 moles divided by 701 moles. So we have 0.1 or 10%. So 10% of the air leaving is CO2. If we want to convert that to parts per million, take this 0.1, which is a fractional value, we're going to multiply by 10 to the 6, or 1 part per 10 in 1 million. And that is equal to 1 times 10 to the 7 parts per million. So this is a fractional amount. This is a concentration in parts per million. For NO2, we have 0.2 moles. We'll divide again by the 701. This is why we went through all of that previous set of calculations to get one number, to get that 701 moles, to know how much air is leaving the system. And that is equal to 0.000285. And then if we multiply that value by 10 to the 6, the concentration is 285 parts per million. So I'm just multiplying this value here by 10 to the 6 to obtain the value in parts per million. And then for
these are the values for what's leaving.
Exactly. These are the concentrations in the gas in the smokestack. So if we were to put a measurement device in that smokestack, we should see these concentrations. And for SO2, same. Again, if we multiply this value here by 10 to the 6, that's 428 parts per million. Okay. You can see, actually, if we think about the coal, that 10%. So 10% of that gas leaving is CO2. And if you think back at how much coal we burned in that 1,000 megawatt power plant, we're producing a very significant amount of CO2. This links back right into when we talk about climate change and the amount of CO2 that we are releasing into the atmosphere. CO2, the carbon is sequestered in the coal, we release it during combustion, and then it's in the atmosphere. Any questions about this? And let's move on. It's the last of these types of problems that we will do. And here we're looking at, and we have a smokestack. And in the smokestack, we determine the SO2 concentration to be 600 parts per million. The velocity of the stack gas is 12.2 meters per second, and the stack diameter is equal to 1.52 meters. You're told that the temperature and pressure of the stack gas are 232 degrees C and 1 atmosphere, and you're asked to determine the mass of CO2 leaving the smokestack. When permits are issued for any sort of stationary source, they're issued on a mass per time basis, not on a concentration. So the first thing we need to think about, you're given a concentration, you're given a velocity, and a diameter, and you're asked to calculate the mass flow rate. In order to do that, I need what information?
Density of the gas.
I will need the density I'll use, and what I'll use in order, essentially for the density, is I'll use PV equals nRT. What else do I need to?
The volumetric flow rate.
Exactly, I need a volumetric flow rate. In order to obtain the volumetric flow rate, or how do I calculate the volumetric flow rate?
V over A.
V over what?
The area
Times the area.
that the gas is leaving.
Yeah, exactly. I just heard, I wanted to check what I said because I heard over, so I was thinking divide. So,
Oh, I think I had that wrong. Yeah, that was my.
yeah, so it's the velocity times the cross-sectional area. So that is 12.2 meters per second times the cross-sectional area, which is pi times the radius squared. Just divide this by 2 and square it to obtain the radius, and that is 22.1 meters cubed per second. To determine the volumetric flow rate of SO2, how can I do that? So this is the volume, this is the gas. So if I want to determine the volumetric flow rate of the SO2, how can I determine that? I have a volumetric flow rate of the gas. If I multiply that by the concentration, it's 600 parts of SO2 per million parts of gas. So the volumetric flow rate of the SO2, should be 3.26 meters cubed per second. So this is, so it's 0.01326 meters cubed per second. That's the volumetric flow rate of SO2 leaving the stack. Now here's where it's mentioned density. Basically what I can do is use this in terms of, I'm going to use PV equals nRT. Essentially, we can relate to density. Density is N over V. The pressure is 1 atmosphere. The volume, I'm going to write the volume as a volumetric flow rate. And you can use those as long as you keep your time units consistent. You can use Q instead of V. Okay, this is a volume, but I'll just per unit time. And that is equal to N. I need the number of moles because I need to convert to mass times 0.082 atmospheres liters per mole Kelvin times 273 plus 232. And I have our temperature. The only thing I have is I have meters cubed on the left-hand side of the reaction and liters on the right-hand side. So I'm going to multiply this by 1,000 liters per meter cubed. So meters cubed cancel, and I have liters on both sides. And then solve for N, and this is 0.320 moles. Now remember, normally you'd have, the answer would be in moles, but I have units of volumetric flow rate, so it's moles per second. So this is moles per second of SO2. So in order to obtain that in kilograms, I have 0.32 moles per second times 64 grams per mole times 86,400 seconds per day in order to obtain this on a daily rate. And I'm just going to convert to kilograms. That's what we were asked for. And this is equal to 1,773 kilograms per day. So this is the mass of SO2 that is actually leaving the stack. We have a few minutes, 2 minutes left, but I think I'm going to end here. On Monday, what we will be doing is we'll look then at estimating emissions. This will very much tie in to Project 1, where you will have to be looking at one of multiple sources. You'll get to pick the source and make a recommendation, but you'll actually have to look at estimating emissions. You'll also have to look at health and environmental effects of these pollutants that are emitted. You have to determine that, and then from that, make a recommendation. So let's end here. Happy to answer any questions that anyone may have. Otherwise, have a great weekend. Remember, homework 1 is due on Monday at 11:59 p.m. Participation 2 is open, and that is due at the same time on Monday. And I will post team assignments and Project 1 this weekend, and that will be due in roughly 3 weeks. February 22nd is what I'm thinking in terms of a due date. So, otherwise, have a great weekend, but I'm happy to also stay on and answer any questions you may have.
Hi, Dr. Masson. I actually had a question about the second example we did. I'm just a bit confused about how we got the 701 number.
Okay, let's look here. Okay, so we have, I'm just going to change color. Okay. So what we want is this set of data provides the masses and moles of the products that are formed. So that corresponds to this information right here. We needed to add 675 moles of air. So that's right here. Okay. But we're reacting. So from this air, what we added, that air contains oxygen and nitrogen. Of that, 94.5 moles of oxygen react, and that we get from right here. So that's how much reacts. So if we calculate that, so that is equal to 701 moles. So we're just doing essentially a mass balance on how much is formed, how much air we enters the system, and then we're subtracting from that air how much oxygen reacted to form these compounds. Does that help?
Yes, that makes sense. I think I was just a bit confused about like
Yeah,
everything that was being added.
It's a lot of information, here, and it's a lot of things to keep track of. So fully understand. So hopefully that helps.
Yes, it did. Thank you.
No problem. Those of you still on, have a great weekend. Happy to also answer any other questions that anyone may have.
I have a quick question. So the team assignment form, is that the one you sent out in an email like before classes started?
Yes.
Okay. I just wanted to make sure I did that.
Yeah, you're good.
Okay, thanks.
Professor, I have a quick question from example 3.
Sure, let's look at that one.
I was just wondering, there's a ratio of 600 divided by 10 to the 6th. I was just wondering where that came from.
Okay, that comes from, let's make sure it's still on the highlighter. So right here, that comes from this information here. So you're given a concentration in parts per million. Think of that as 600 parts per million parts, and it's on a volumetric basis. So for every million liters of gas, okay, in that million liters of gas would be 600 liters of SO2.
Okay, that makes sense. Thank you.
So that's why it's 600 out, and it's just easier to write it as 600 over a million. At least it's consistent with the definition.
Okay, thanks.
No problem. Any other questions?
Dr. Maston, I didn't get to finish writing the end of problem number 3. Do you mind just going back to that really quick?
Not a problem.